welcome to lecture 6 of computational geometry. So, we will continue with our example that we started last time on computing the area of union of rectangles, isothetic rectangles, that is axis parallel rectangles. And again the technique that we are using, the main technique that we are using is the line sweep. You look at this example where there are a number of overlapping rectangles. This situation of course is more complicated than the situation where the rectangles are non-overlapping, in which case you simply just compute the area of individual rectangles and add them up. As we had observed last time, we can try to reduce this situation where we have overlapping rectangles to the situation where it is non-overlapping by actually trying to compute all the intersections. Okay. So, if we can compute all the intersections, then we can think about them. So, these intersecting rectangles can become the smallest intersecting rectangles which do not have any further intersections, they become your disjoint set of rectangles, and thereby again you can compute the total area by just summing up the areas of these rectangles. Unfortunately, if we try to do that, then we will have to compute these intersections, and there can be lots of intersections. Namely, if this is the case, there are close to about n square intersections. So, then your chances of a sub-quadratic algorithm is no longer there, right. So, we would ideally like to compute this faster than something like n square time, where that is we want to avoid computing these intersections, right. So, what is the basic idea that we started pursuing? So, again if you want to use line sweep, and as we start from the leftmost rectangle, and as we sweep across at any point of time, we maintain the intersection of the rectangles with this sweep line. And if you look at this delta x, so this infinitesimal that I am sweeping, whatever is the total area that is being swept by this line, okay, we can write this as summation of. So, y is the total intercept of the rectangles with this vertical line, and therefore, this infinitesimal area, the rectangular area would be y times delta x. And so, if you sum it up from x equals to the leftmost rectangle, let us call it r, and let us call it L and R, left and rightmost, then it is basically the measure of the union of the rectangles, right. So, this y that we are saying multiplied by delta x, we can write this only if this y, which is the intercept of the rectangle. So, here in this line, the intercept is essentially this plus this. So, as we sweep past, we do not want this y to change. Okay. So, our stopping points, so the event points will be those where y x coordinates such that there is no change in the intercept, and then we can write this equation, and thereby we can compute the total area. Okay. So, this actually introduces a problem which is actually now one dimensional in nature, right. It is the total intercept of the rectangles with this vertical line, right. In other words, so I will just sort of rotate the axis. So, what we are now trying to do is, given a set of intervals, they are actually all they are all along the x axis. I just spread them apart so that they are visible. So, I have a set of intervals, okay, and I want to compute. Okay, I will take a. Okay, I will just change this example a little bit. Create more gaps actually. Right. Okay. So, we have this set of intervals, let us call them I1, I2, I3, etc. to some I sub n. So, we are given these intervals along x axis. Of course, in the actual problem these intervals are along y axis, right. And we want to compute the the sum of the union of intervals. Okay. Namely, in this particular case, the sum would be well, this is covered. So, I will just use another color. So, this part is covered, okay, and this is, let us say, some number, say say 1.5 or something, and then this entire thing is covered by at least one interval, and there is this again some gap. Okay. Then again we have this and this and this, right. So, if I had actually not drawn these intervals separated in the y direction, this is what it would have looked like. Okay. And what I am interested in is the sum. So, maybe this is 1.5 and this is 3.8 and this is 2.2, something like 4, maybe something like 1.9. Right. So, then I will simply add these up, these are disjoint intervals, okay, and whatever is the sum, that is what I mean by the sum of the union of the intervals. So, when we are talking about computing the area of the rectangles, okay, using this plane sweep method, we have now actually reduced the dimension to a one dimensional problem, because we are only looking at the intercept of the rectangles with a line. Okay. So, now we can only look at these intervals. These intervals are nothing but, you can think about them like the projection of the rectangles on the y axis. Okay. In this case, of course, I have turned the coordinates around and it is the x axis. Fine. So, once we know this, and this is essentially our y, this 1.5 plus 3.8 plus 2.2 plus 4 plus 1.9 is what is y equal to. Okay. And if we sweep by amount delta x, okay, if we sweep by delta x, where y does not change, okay, then the total area swept by the horizontal by the vertical line equals whatever whatever the sum is, y times delta x. That is all I am saying. So, it appears that, so we have now reduced the problem of computing the area of rectangles to one where we want to compute this, keep track of this y, where y do not change, and y only changes, y will change, or let us say y can change, I should say y can change only when one rectangle begins, okay, and two rectangle ends. And unlike our segment intersection case, both these events are known to us right from the beginning, because the rectangles are given to us. We are not trying to compute anything that is related to the intersection of the rectangles. We are only looking at the beginning, that is the left boundary of the rectangle and the right boundary of the rectangle, that is all. Okay. So, these events are well known to us in advance. Okay. So, the actual work or the actual algorithm focuses around computing this y. Okay. So, how do we keep track of y? Okay. This is essentially what it comes down to now, which is what, as I just pointed before, it's a set of intervals, okay, and what is the sum of the union of these intervals. Okay. So, how do we keep track of this? What would be the simplest way of doing it? I am given a set of intervals, given a set of intervals. Something like this. So, how should we keep track of the sum of these intervals, given that two intervals can overlap? Yeah, I think someone said that. So, we can use another sweep kind of technique, which is, see, when I started drawing these intervals, I was actually drawing it in kind of a sorted fashion, the left to right. I took the leftmost endpoint, okay, drew this interval, okay, and then shifted my pen and drew the next interval, which means that the next leftmost point, and I drew it in that order, and actually this is also the method by which I can actually keep track of the sum of the total length covered by these intervals. Okay. So, this could be something. So, as we start sweeping from, again, if I start sweeping from, this is a one dimensional problem, but I can just start walking along the x axis. This is my x axis. You can simply start walking. Okay. So, as long as, so we picked up this leftmost interval. So, we go on, so we keep track of the fact that we have picked up some interval, okay. And if we encounter, we first saw what do? We first sort the endpoints of the intervals, right. So, let us say we sort the endpoints of the intervals. Okay. So, there are two endpoints to be sorted, okay, two endpoints, fine. I do that, and then I start walking from the leftmost interval, the leftmost endpoint of the interval. And as we walk, I have to keep track of the fact that at any given point of time, is there any interval covering that x axis. Okay. So, as we walk along this x axis, so I keep walking because this interval has not ended. So, we also keep track of, use another color, as we walk from left to right, we keep track of, is there any interval covering a particular x value. Right. So, as I walk across, so I can continue because I have not encountered the right endpoint, which means that there must be some interval covering every bit of this journey, or whatever this movement from left to right. Okay. Now, of course, this segment ends. The moment it ends, here there is a gap. So, there is nothing that is covering it. Right. So, whatever I have covered till now, I can make a note of that. Okay. Maybe it is, as I said, maybe it is some 2.2 or something like that. So, somewhere I am going to count that I have swept 2.2. Okay. And then at this juncture, there is no interval covering this. Okay. So, I have to now jump to the next endpoint, which is here. Okay. Again I start walking, great, I note down this whatever this left endpoint, whatever that x coordinate is. Okay. So, again I start walking. Of course, we do not walk continuously, you only walk to the next event point, which must be an endpoint of some segment. So, here it happens to be the starting endpoint of another segment. Okay, great. So, what it means is that, so as we walk, we not only keep track of the fact that there is an interval covering it, we may also want to keep track of the fact that, so I have encountered this, okay, but then there is still another segment covering as I walk past that. So, what should we also keep track of? Number of intervals covering any given x coordinate. Okay. So, that we always keep a count.
So we can do it simply by implementing a stack. Whenever we encounter a begin point of any interval, we push something into stack, and when we encounter an end point.
See, stack is a very, it is a data structure which is only last in first out. These intervals may not have the last in first out kind of property. An interval, two intervals can be related by any kind of relation.
That's one thing. Whenever you encounter an event point, if it's a begin of some segment.
So, what is that you are going to push and pop?
If the stack is empty, you don't walk.
No. So, why do you need a stack? I am just talking about a counter. A simple counter will do, right? Okay. All I am saying is keep a counter to note how many intervals contain the present x coordinate. Okay. So, then if a segment ends, an interval, we are using the word interval, sorry. If an interval ends, decrement count, interval begins, increment count. Okay. So, this is the simple thing about the count, and we must also keep another kind of a global counter where we are going to add how much x coordinate, what is the measure of the x coordinate that is being covered, right. So, only when the counter reaches 0. Okay. So, here for instance, we have started from this left end point. So, we make a note of this x coordinate, suppose it is some 3.5. Okay. So, we know that the last endpoint that we started with for when things are actually covered by some interval, okay, to wherever this ends, the count also becomes 0, right. Count is 0 at here. So, count equal to 0. So, when the count equal to 0, we also note what is the x coordinate of this, maybe it is 6.3, okay, which means that we have swept 6.3 minus 3.5, and this must be added to the total measure that we have encountered so far. Any doubts? This is the most straightforward way that you can do it, right. So, what is the overall sort of complexity that we are encountering in the process? So, at the end of the whole thing, we should give the correct measure of the the union of the intervals. Order n without counting the sorting cost, right. So, if things are sorted, then it is order n. We are not doing anything, any work. Every event point, we are just incrementing or decrementing the counter, checking if the count is 0. If the count is 0, then we must do this subtraction and keep it aside. If the count is not 0, we just continue. Okay. So, this is nothing but actually the one dimensional version of the area problem. Here we are computing the measure of the union of the intervals. There we are actually computing the actual problem was to compute the measure or the area of the union of rectangles. So, using the line sweep method, we have somehow managed to reduce the dimension, which has actually, let us say, made the problem at least more easier or more straightforward, right. And then we put these things together that so we know how to actually at any in the original problem. Okay, let me go back to the original problem. In the original problem, actually we are sweeping a vertical line. Okay. So, at any at any x coordinate, okay, just by the previous approach we can compute the total intercept of the rectangles with this line, okay, and then we can keep sweeping till we encounter the next event point, which is either the beginning of a rectangle or the end of a rectangle, right, and then multiply whatever distance we have traveled, that multiplied by the total intercept, which is constant because it cannot change between two event points, and then we eventually we sum up everything and we should get the right area. Okay. So, what is being observed here is the total complexity should be n square. Why is the total complexity n square? So, let me just note what we noted essentially is that to compute y is solve the one dimensional problem i.e. the sum of the union of intervals, okay, again by some kind of by line sweep method, let us say. Okay. So, we noted that this takes if you are just looking at all these instances as independent problems, to compute this intercept with the y axis, okay, this could take about order n log n time if we sort, okay. And then there are 2n event points for corresponding to the left and right vertical boundaries of the n rectangles, right. So, at every event point, if you do it naively, or in the straightforward way that we just did it, so that is n log n. At every event point we may have to update this essentially, right. So, the straight if you just do it naively, then you get this this thing about order n log n times 2n, that is someone said n square. So, it is pretty close to n square, let us say n square log n, right. Fine. So, we are unfortunately back to the same complexity if we were to actually compute these intersections and treat them as disjoint rectangles, but we wanted to avoid all that. Okay. However, note that all this is done assuming that these every time we have to compute we encounter an event point corresponding to the beginning or the end of the rectangle, we are computing the sum of the intervals from scratch. Okay. But the reality is that when we encounter the left or the right boundary of a rectangle, okay, exactly, and let us again assume that no two left or no two right boundaries are on the same vertical line, okay, then actually exactly there is one interval that is going to get deleted, okay, here. So, this rectangle ends, so this gets deleted, or corresponding to here there is this rectangle, this interval corresponding to this rectangle gets added. Okay. So, at every event point the change is very incremental, okay, and trying to sort of run this entire one dimensional algorithm what I mentioned is something that hopefully can be avoided, because we have a lot of information corresponding to the remaining intervals. It is just that one interval, okay, we have to take care, either we have to, so either we subtract that one interval or we have to add that one interval. Now, that may or may not make difference to the intercept, okay. But all that is essentially again with it's just one interval that we need to somehow handle, okay. So, it is some kind of a dynamic situation, right. It is not fully dynamic. I am saying it is not fully dynamic because these intervals are known to us in advance, the rectangles are given to us in advance. So, it is not that this one dimensional problem we are just arbitrarily introducing some interval like this, but this interval is known to us because it has to be either the right boundary of a rectangle or the left boundary of the rectangle, and it is available as the initial input. Okay. So, it is not a completely arbitrary interval. So, we have fair amount of information available and we should be somehow able to exploit that. Okay. So, yeah, so right. I mean, the idea is that, so what area? So, now the question is that if we keep track of somehow that this part of the x axis, okay, is covered by this interval, and if this interval disappears, okay, then we should update something. But it is not such an easy thing to do. Okay. I will give you a very bad example. It is not an easy thing to do because we have to now keep track of, first of all, it is a continuous information. I cannot keep this information for every x coordinate. Okay.
But this interval will only affect those intervals which it is, or with which it is intersecting, right?
Yeah, yeah. So, here this x coordinate, okay, is covered by these two intervals. The thing that I am trying to point out is that which of these x coordinates should I keep track of, because there are infinite number of x coordinates. Right. So, the information remains unchanged, let us say, in this whole thing, right. And what is observation here, that it must remain unchanged between two event points, two consecutive event points. Okay. So, we have to deal with, okay. So, now let me expand this figure. So, if we have lots of intervals, okay, we have to deal with the relevant ones are corresponding to these endpoints, and so if I take this to be my x axis, so these event points corresponding to endpoints. So, between any two consecutive event points, the information is fixed. We know that these are exactly the 2 or 3 or 4 whatever segments intervals covering that x coordinate, okay. So, or that this interval, okay. But if you keep track of this information also, suppose I have a situation like this. So, then what means, it means that I have some intervals, I have 2n intervals, right. I have 1, 2 all the way up to 2n intervals, okay. So, for each interval I keep track of, okay, which segments cover it, okay. So, interval 1 is covered by segment 1 and segment 2. So, 1 is covered by segment 1 and segment 2, 2 is covered by 1 is only covered by segment 1, I am sorry, 2 is covered by segment 1 and segment 2, okay. 3 is covered by segment interval 2 or segment 2. So, this is the kind of information that we have in mind, right. The bad thing about this, so therefore, if there is something that needs to be updated, okay, if I delete or add a segment, we know exactly which of these intervals are going to get affected, but then a large number of intervals could get affected, right. And not only that, this information itself has a bad, you have a situation like this, suppose, okay, what it means is that so for each interval there could be a large number of segments covering it, okay, which is in fact if you do this there will be at least about n square kind of information that you need to store, right. So, if I need to store n square information again, I do not have much hope about an efficient algorithm. Okay. So, although this kind of information can be maintained in this way that which, and these intervals are known to us, that is we know that which we know the rectangles, we know the boundaries, and therefore, we know all these intervals in advance, these 2n intervals in advance, but still updating that, okay, could be quite expensive, because a single segment or single interval can cover a lot of them. So, if I have to keep it updated whenever I encounter the right boundary or the left boundary, okay, it could still mean lot of work, and it could be, let us say, about order n work per update, okay, where I have given you this kind of an example, and therefore, again you are back to this n event points, each update takes order n time, you are back to the order n square situation. Okay. So, we have to be much more clever about this data structuring part, or then how do we actually do these updates. Okay. So, how do we do these updates? So, for that we will actually make a few observations. So, these are these intervals. Okay. So, there are these intervals 1 to 2n. Okay. I will try to define a kind of a so, one is that let me number those intervals. Okay. So, well, I have done it here 1, 2, 3 up to 2n. Okay. Take a fresh page. So, I have some kind of interval 1, 2, 3, 4, 5, 6, 7, 8. Suppose I have only 8 intervals, just for an example. Okay. I will define a kind of a a tree kind of a structure associated with this interval. Okay. So, I will treat these 8 intervals as leaves of the trees, let us say. Okay. So, I have okay. So, this leaf is associated with this interval, this leaf represents this interval, this leaf represents this interval, and so on and so forth. Now, what the actual intervals are, the lengths etc., that information I can store, right. But now this will be more of a combinatorial representation. Okay. So, what the lengths are, whether they are equal or non-equal, it will not make any difference to the structure of this tree, right. So, this interval this interval corresponds to this node. Then I will define the parent of these 2 leaf nodes, okay, which will be the sum of the intervals that the 2 children represent. Okay. So, this one will represent essentially the entire interval from here to here. Okay. This represents only this much. Okay. Similarly, for these things. Right. Now, this one, the parent of these 2 nodes, will define and represent this entire interval. Okay. So, this one represents the entire interval, and of course, there is now the root of the tree represents this entire interval. Okay. So, I have a certain number of intervals, just for again for simplicity, we are assuming it is a power of 2, so that I can define this tree very easily. Even if it is not a power of 2, you could just either have some empty things, or you can make it almost balanced, that everything, all the leaf nodes will be within one level of each other. Right. Now, so this yeah.
Here we are not keeping for every interval, right? Like 2 to 3 we cannot.
Okay, so that will come to that. So, right now, these are what are called canonical intervals. What is a canonical interval? The canonical intervals are exactly those represented by the leaf nodes. So, not leaf nodes, by any node. So, this is a tree which has how many, about 15 nodes, right, 8 plus 7, right. So, this 15 nodes, okay, represent 15 intervals which I am calling canonical intervals, namely. So, the leaf nodes represent these if we call it n, the n nodes, okay. The ones above the leaves the parents of them represent, let us say, n over 2, and there are again n over 4 and etc. So, essentially this tree structure is able to represent only a linear number of intervals, right. Any node of the tree corresponds to some interval, and the total number of representable intervals using these nodes is only n plus n over 2 plus n over 4. So, some order n, let us say 2 n or something. Okay. So, we are still fairly restricted, and the question that came was, what about an arbitrary interval? Suppose I want to represent this interval. There is no node in the tree that represents that interval. How many intervals can be there? Possible intervals according to this structure? About n choose 2, right. I mean I can choose any 2 endpoints among these endpoints. So, there are n choose 2 possible intervals. Okay. These are not arbitrary intervals, these have to, whatever intervals we consider must be flush with one of the endpoints. I am not thinking about representing something like this from the middle of this to middle of that. I am only thinking about representing intervals that span two such points of this, because these points are known to us. If you think about the original problem, these points are known to us. So, any interval will span, they are not arbitrary intervals, it has to span two such event points or end points, whatever you call them, right. So, if you restrict your intervals to be those kind of intervals, then I can choose any 2 points and that represents an interval, and that is basically n choose 2. So, we have only order n canonical intervals, okay, and we need to somehow deal with order n square intervals. How do we do that? If we could do that, then I claim that our problem, or well, I mean that's basically what we are trying to do. I mean, have a nice way of representing these intervals, so that we can do these deletions and insertions of the intervals easily. So, let us look at this one interval that I just pointed out, this interval. Okay. So, clearly it cannot be represented by one node, but we should be able to somehow represent it by some union of some nodes perhaps. So, what do you think, which ones should we use to store this interval?
Can we decompose this as a union of canonical intervals?
Yes, that is what I am saying precisely.
The leaf 4 and 7 and the union of 5 and 6.
Okay. So, let me use another color. So, if I want to represent this interval, are you saying that I should store it here or this node, okay, and which other nodes?
5 and 6 the union.
That means that one,
I should store, I have a choice of this and this also, right. I could okay, I could do this and this, and I am done, right. If these are, but these are all elementary intervals essentially, these are the intervals of the leaf nodes, but then if I use leaf nodes, there are too many leaf nodes, okay. So, especially if I have both leaf nodes or both 2 nodes that they are used for the storage, I might as well substitute them by the parent, because then I save something, right. So, if both these nodes are required, then I am not going to use that, but rather use the parent, okay. So, I should use this. So, here also I cannot use this and this, so I can only use this. So, I will store this, and then of course, I do not have anything else. So, I will store it like this. Okay. Suppose it were the case that this was all to use, then I would not have used this, and I would have stored the whole thing here. So, if both the children are storing, then I will not use them, but I will use the parent. Okay. So, therefore, you can see the storage structure of an interval is such that you are not going to store them in 2 nodes which are ancestors of each other. Yeah. So, so the the answer comes very quickly. Then it's the total number of nodes where that is required to store any arbitrary interval is about order log n, and so we'll have to justify more carefully. But if this is true, then it's great, because now you see that an interval, okay, if you can use if it can be stored using only order log n intervals as nodes of this tree, okay, then I have to, when I am adding or when I am deleting, okay, I have to at most update order log n nodes of these trees. And what do I mean by update? So, eventually I would like to, I have some intervals, right? I have some intervals, not just one interval, I have some intervals, okay, maybe this interval, this interval, this interval, etc. Okay, and I want to find the total measure of these intervals. Okay. I am going to store them in some nodes, okay, and I want to compute the result in the root node somehow. So, that is how I am going to basically keep track of the total measure of the union of the rectangles. Okay. And how is this done? Okay. If there is some interval that is stored here in the root node, okay, this is, by the way, an actual tree, right? I mean, our computer science trees are usually like this. Okay. I could have written like this. This is actually growing out of the ground, right? So, anyway, so this is the real root. So, if there is any interval that is stored here, that is this is also colored, which means that this interval, there is some interval corresponding which is stored in this node. It means that the measure of the sum must be this entire thing, all the way from this 8, whatever it is, the left endpoint to the right endpoint. Of course, each of these endpoints has a coordinate actually. So, whatever it is, that entire length would be my measure, because there is something being stored here, if there is something stored here, right? But it may not be the case. If it is not the case, then there is nothing stored here, then what should we do? Then it must be the sum of what is stored here and what is stored here, because these are disjoint. Okay. So, whatever is the total measure stored here and the total measure stored here, it will be the sum of that. Right. So, if we basically just go through this tree and we have to visit every node, we can easily find out what the total measure is of these union of these intervals. Right. So, that will be order n if you were to compute this, right. But then we do not have to compute the entire thing, we only have to make updates. In our context, what are we doing? We are only either adding an interval or deleting an interval. Okay. So, we do not have to visit all the nodes for doing that. We only have to visit those nodes, okay, which are either added because of this thing, okay, or deleted because when this gets deleted, these things, this storage basically is thrown away. Okay. So, then and since we are dealing with only order log n nodes, okay, we can do these updates in time proportional to order log n and the height of the tree.
Sir, can you explain why this will be order log n? I mean, you said that there cannot be any ancestors. I mean, they cannot be
Yeah. So, I'll come to that, and I'm just giving you a summary of I'm giving you a feel for why all this is good, okay, and then we'll do the precise reasoning. So, if what I am saying is correct, essentially you have an algorithm where every update will cost you order log n, okay, corresponding to each event point, and there are 2n event points corresponding to the left and right boundaries of rectangles. So, therefore, the whole thing will work out in n log n time, right. That will be absolutely great. Okay. So, now let us take these things one after the other. Why is it true? Why do we claim that there are only order log n nodes that will be where an interval can be stored? Okay.
So, because there can be at most 2 nodes at each level, because if they are consecutive, then 2 will be
correct. So, that's a fairly accurate reasoning. So, what is being said is that look at any level of this tree corresponding to any interval, okay. Because this is a continuous interval, you can have at most 2 nodes that store some part of that interval, some sub-interval of that. Right? I cannot have the situation where I am storing something here. Okay. So, one is that if you have two consecutive things, it must go up to the thing. Okay. So, we cannot have the situation where we have something and gaps and something like this, right, because it is a continuous interval. Right. It cannot have there cannot be a gap, because then there must be some storage here also. If there is a storage here, then these two should combine and move up. Right. So, there can be at most two storage nodes corresponding to an interval at each level, okay, and there are only log n levels. So, there are at most 2 log n. Okay. So, what we have argued is that there is less than or equal to 2 log n storage nodes for any interval. So, if that is the situation, then why is the update order log n? Does it immediately imply that the update is order log n? Not really. See, if you think about it, here is a node. Okay. When we want to update, we have to basically walk along this node to the root and update the counts, right. Each node could have one or more intervals. As long as it has an interval, it means that it covers the entire interval corresponding to this canonical interval. Okay. If the count is 0, okay, then it must be the sum of these two. So, whenever we have a new storage node, or whenever we are deleting something, okay, from a node we must actually start walking towards the root, updating all the counts. Right. So, if there are 2 log n storage nodes, okay, what does it imply? It only implies about log square n, right, because for each node you have log n updates. So, for log n nodes you have order log square n updates. Right. This would be the naive reasoning, but actually there is more structure to it, which makes it actually an order log n update rather than a log square n update. It may not be clear exactly from this example. So, I will give you another example, maybe from there it will become clearer. So, this is something that okay. So, it is something that I drew before I came to the class. So, let us look at this. Is it visible or not? Should I draw it? Oh, let me draw it in case, okay, because it may not be visible in the camera. Huh? Okay. So, I have drawn something corresponding to the these intervals 4, 5, 5, 6, these are my elementary intervals 6, 7, 7, 8, 8, 9 all the way to 14, 15, and I have a tree like this. Okay. And you look at this interval 10, 13. Okay. So, this is I have drawn it in the proper way, the tree, the root is at the top. Okay. So, if you actually now, so we argued that there are about 2 log n storage nodes for each interval. Okay. Now, we will actually be able to argue something about the structure of these of the node. They are not arbitrary log n nodes. Okay. So, if you look at this interval 10, 13, okay, it kind of spans this. It kind of spans this. And how do we actually, if you are given this tree and I have to find out where we should allocate, where are the allocation nodes, I take this 1013 interval, okay, and look at the. So, this is the root node which corresponds to the entire interval from 4 to 15. Okay. So, 1013, you know, and we see that actually this 1013 corresponds to. So, this entire interval will lie to the right on the right subtree, because the left subtree only goes up to 9. Okay. So, for every node I'll actually store a kind of a dividing point. Okay. Here it is 9, okay, here it is 6, and so on and so forth. Okay. Now, this entire interval 1013 lies to the on the right subtree. So, we actually basically come here. Okay. So, when we come here, and if this were a bigger example, it could be that this entire interval lies to one side. That could be the case. Okay. So, for a while maybe this entire interval basically travels down, okay, for a few levels of the tree before it hits some node where some part of it is to the left and some part is to the right. Okay. In this case, it happens that at this node itself, you know, which we call this a forking node. So, it forks basically. It forks, okay, and after it forks, you know, things are very regular. So, this is so we have 1013, and if you look at it, this is an allocation node, okay, and this is an allocation node, right, because it covers both 11, 11, 12. Of course, they happen to be at the same level. So, the structure actually, again, if I had a bigger example, that would become clearer, but now I'll just abandon that and just show you, you know, what is basically happening. So, if you have any tree, okay, this interval that we are looking for, you know, you travel, the entire interval travels for a while together, okay, and then it forks. Okay. And after it forks, okay, you can only have one kind of pattern, the worst case pattern or whatever. One kind of pattern is that you will have something like so there will be some path. Okay. So, you look at the left path and the right path. So, each interval, let me come back here. So, you look at the left end point of the interval and the right end point of the interval. Okay. So, 10, you just locate, you just try to find where 10 lies, and 10 will take you basically like this, and 13 will take you something like this. Well, yeah. Right. So, these are actually the two endpoints will trace this kind of path in this tree. So, which side the point falls on? So, after all we are talking about, you know, whether the point, for every node we have a dividing point. So, if the point goes left, the path goes left.
Why at that junction 13 was also the right interval, but why didn't we take that?
13 was,
I mean, I think that was 12. The left also has the
this one?
no, the node before that.
This one?
Yeah.
You could have taken left also, right?
Yeah. So, actually strictly speaking, you know, this 13, you know, this is actually an open interval. So, you know, the intervals are actually something like, no, I should have pointed out, it is actually something like A O P. Okay. This is strictly speaking, it is like this. Right. So, we actually we can trace out two paths, okay, for the left endpoint and the right endpoint of the intervals, and this will be paths like this. Okay. And so, there is some path and there is some path, okay, and you can actually, you know, this is something I will leave for you to, you know, convince yourself. Your allocation nodes will be exactly this: the the right child of the left path and the left child of the right path. Okay. And because this is the case, so when you actually walk up from there, you know, these paths actually merge. So, you are not dealing with, you know, order log n distinct paths, but they are basically, you know, have a very nice pattern. So, I am not going to, I am going to only deal, I am only going to visit order log n nodes on my way up from each of these nodes. The total number of nodes that I visit will be order log n. Okay. So, total number, or maybe I should write it here. Okay. So one observation is that so this structure I should say is about, these are called interval trees. Okay. Observation over interval tree. So, whatever I drew corresponding to the interval is called an interval tree. Okay. So, one is each interval is stored in at most 2 log n nodes, okay, and 2, the total number of nodes visited when we walk towards the root from the allocated nodes, okay, is again less than 2 log n. So, this is what actually makes the update, not even log square n, but log n. Okay. Now, you can put everything together. So, so let me just summarize before I end. So, what we did today was we took this rectangle problem, okay, and did the line sweep, and when we did the line sweep, the problem came down to how do we keep the intercepts updated when we sweep between 2 consecutive event points defined by the left and right boundaries of the rectangles. Now, for performing this update of the intercept, okay, we looked at the one dimensional problem, which becomes essentially we are given a set of intervals. Now, if I add an interval or delete an interval, okay, how do I update the measure? And for that we define these interval trees, okay, where the elementary intervals are consecutive points. Okay. So, leaves correspond to elementary intervals, and every internal node corresponds to a union of its children, okay, and that is how we define the tree. And if there is so these the nodes corresponding to the trees correspond to about order n canonical intervals. Now, to represent an arbitrary interval, okay, we figured out which are the storage nodes for that particular interval, and then we observed that there are at most 2 log n allocation nodes for each interval, okay. And moreover, not only that, these allocation nodes for each interval have a very nice structure. So, that so basically the structure corresponds to this, that when you walk up from these nodes towards the root, you are not going to visit more than again about 2 log n nodes. So, this entire thing therefore gives us a order log n update time for adding or deleting an interval, okay. But beware that this is not a completely dynamic process, because these intervals are known to us in advance. Okay. I can't deal with an interval whose endpoints do not coincide with these endpoints. Right. But in the context of the rectangle problem, we know all these things, and therefore, the entire thing about the line sweep on the rectangles and computing the area will work in n times. Each update will take you order log n for each event point, and the whole thing will be order n log n. So, we can compute the area of the rectangle in order n log n time. Okay. So, we will end here today.